Good day everyone. We are Sydney Group 17 and today we will be presenting our project titled Comprehensive Heart Disease Prediction using Machine Learning and Deep Learning Models. The purpose of this project was to apply data science techniques to an important real-world issue, heart disease, and to evaluate which models work best for predicting patients' outcome. Over the course of this presentation, we will introduce you about our projects and also explain about our datasets we use in these projects. And we talk about the pre-processing steps, the algorithm we used, and the performance of these models. And finally, we will talk about the conclusion and insights we gain from these models. Heart disease continues to be the one of the leading cause for the death worldwide. Early detection is vital as it greatly improves patients' survival and the quality of life. Traditional diagnosis methods often require multiple tests and can vary depending on the doctor's interpretations. This creates an opportunity for the artificial intelligence to play a supporting role. AI models can quickly analyze large amounts of patient data and provide predictions that help doctors make faster and more accurate decisions. In our project, we focus on three main objectives. First objective is to compare traditional machine learning with the deep learning methods. Second is to evaluate both approaches on the same datasets. And third, to identify the algorithms that derives the most reliable predictions with the accurate output. For this study, we used the UCI heart disease dataset from Kaggle, which is one of the most widely referred datasets in the cardiovascular research. It contains over the 1,000 patients' records, its records with the clinical features. These features includes demographic factors such as age and sex, as well as the medical indicators like chest pain type, resting blood pressure, cholesterol level, fasting blood sugar, and maximum heart rates, and the exercise agina. These target variables indicates whether or not the patient has heart disease. What makes this dataset particularly useful is its mix of categorical and numerical features, which allowed us to test different algorithms and see how they handle various type of data.
Let's proceed to transformation and data preprocessing. Before we could train our models, we needed to clean and prepare the dataset. Here are the key preprocessing steps we perform: encoding categorical variables, such as sex, chest pain type, resting ECG, and ST slope, converting them into numerical form for the algorithm to understand. Checking feature correlation with the target variable to identify which factor most strongly influence heart disease. Splitting datasets into 80% for training and 20% for testing, ensuring stratification so both sets have a balanced number for positive and negative cases. Normalizing numerical feature using standard scalar, which help models like KNN and SBM perform better by keeping all variables on a similar scale. During this step, we also created visualization like age analysis and target distribution. You can also see here the categorical feature visualization: sex, chest pain type, resting ECG, exercise angina, and ST slope. And in here, you can see the visualization of correlation matrix and target correlation bar. This visual gave us a better understanding of the data before modeling. Let's proceed to algorithms and model overview. To compare different approaches, we use a combination of traditional machine learning algorithms and deep learning models. The machine learning algorithms included logistic regression, k-nearest neighbors or KNN, decision tree, random forest, naive-bayes, support vector machine (SVM), XGBoost, both basic and tuned version. For deep learning, we built a multi-layer artificial neural network (ANN) and a long short-term memory network (LSTM). Why these algorithms? Traditional, traditional machine learning models are lightweight, interpretable, and work well on structured datasets. Deep learning models like ANN and LSTM are more advanced, capable of capturing complex patterns but require larger datasets. Training strategy. We use 80-20 train set split for initial evaluation. In addition, cross-validation was used for some models to ensure consistent performance. Here is the detailed analysis decision tree. You can see the confusion matrix and key performance matrix. For this one, the detailed analysis of random forest, confusion matrix, and key performance matrix. And this one is the detailed analysis of naive Bayes, confusion matrix, key performance matrix. This is a detailed analysis of multi-layer, and this is the detailed analysis of LSTM, or long short-term memory network.
Thank you, team member, for completing your slide. Now let's move on to this new slide that is a model performance and evaluation. Let's examine each of our nine of our models and which work best and with some of the reasoning as well. For a medical application, we focused on a F1 score because it's important metrics and it's like forces a balance between a precision and precision normally used for avoiding a false alarm and the recall, which makes sure that we don't miss any diagnosis. That is the most important thing in the medical field as well. Uh, Now let's take the model, one of the model for the example, that is the advanced model, advanced deep learning model, LSTM model. We can see it achieve and fantastic like recall of like 0.931, meaning it was excellent at identifying the true diseases cases. However, it overall shows the F1 score of 0.892, which tells us that it has produced a slightly more false positive than the other top contender. This shows that the critical trade-off inherits in the clinical modeling as well. Now, let's move to this one, that is the comprehensive model comparison, and which one is the most unexpected winner as well. When we conduct a comprehensive evaluation and the model comparison, we compare on the basis of sorted by F1 score. And what we found surprisingly is that the top performer was the naive Bayes algorithm, which achieves the highest F1 score of 0.9208. This relatively simple and traditional algorithm, which delivered the most balanced and effective performance overall. uh, Knife base is the simplest and the traditional method. Even though we are using the advanced deep learning method, knife base comes out as a top performer. Now let's look at the other critical competitor as well. We have certain competitor. First one is the support vector machine, which was a very close second with an F1 of 0.9151. It actually achieved the best absolute best recall at 0.9510, and all the three best modules including random forest 0.8942 and the tune XGBoost 0.8922, which are highly stable and robust. Our deep learning module, the ANN 0.9038 and LSTM 0.8920, were competitive, but importantly, they were not superior for this data set size. This analytical result forces us to question the complexity. Biased in the case of like simplicity, and interpretability gives us the predictive power as well. Now let's move on to this radar chart, which visualize the different metrics performance. This radar chart beautifully visualize our central finding. It's an effective tool for comparing our model because each axis represent a key metric such as accuracy, precision, recall, and F1 score. The goal for any model is to create the largest shape on this chart as it indicates the balanced high performance across all four metrics. As we can see, notice how the lines for the knife base, the thick blue lines, and the support vector machine, the light blue lines form the largest quadrilateral stretching closest to the outer, 1.0 boundary on all of the axes. This visualization confirms that their status overall perform the best. This visualization confirms that the status as the overall best performers. In contrast, we can see that the deep learning model like LSTM, Redline, and the tree-based models like XGBoost and Random Forest sit just slightly further inwards while they perform well, but this chart can clearly confirms that for this clinical data sets, traditional and the simpler models are the most versatile and high performing across the board. Now let's jump to this final slide, which is our conclusion and key summaries. Let's finalize our presentation by detailing the implications of our study. We have like three critical takeaways as well. First one is the simplicity when challenging the complexity bias. Our most significant finding is that the simplest and the most explainable model, naive Bayes, was the best performers, which achieved 91.30% accuracy. This is like a powerful demonstration that for a structured clinical data, traditional machine learning can meet or exceed the deep learning method as well. This is not just a technical finding, right? It's like a practical one as well. The simpler the models, it's easier to like get the trust, regain the data, and everything. So, like same in the medical field, it's it's like practical one, like a simpler model are easier for clinician to trust and for regulator to approve. And second one is the actionable intelligence and feature importance. Like we didn't just build the module and realize which one has the highest precision, accuracy, or all, but we gain some insight and we gain the knowledge of how modules works and their critical factor as well. Those critical factors driving the prediction like more consistently identify as three critical factors. I find it more. First one is like chest pain type, and second one is the age, and third one is the maximum heart rate. These provide like a clear and actionable guides for doctor highlighting where the diagnostic focus should be rely on. And the third one is the model robustness for the real world deployment. Uh, Beyond peak performance, our study find out that all the models exhibited good generalization. Furthermore, assembles methods like random forest provided robust, reliable result. This means that while naive Bayes wins on F1 scores models like random forest offer a highly stable alternative for consistent deployment. Ultimately, we have achieved our objectives. We have a comprehensive validated model comparison, proving that the effectiveness of a model depends entirely on a dataset characteristics. Thank you. Now we come to the end. In closing, we want to leave you with this thought that the pursuit of the complexity doesn't always guarantee the superior intelligence. Our research confirmed that the best solution for early heart disease detection is the one that is both high performing and easily understood. Thank you. We have provided a comprehensive analysis and we encourage you to review our project. Thank you.